My dear young students, scientists are constantly discovering new compounds, orderly arranging the facts around them, trying to explain with the existing knowledge, and organizing to modify the earlier views or evolve theories for explaining newly observed facts. So, my dear friends, let us together explore and understand how the atoms are held together in chemical compounds. You know that matter is made up of one or different types of elements, and under normal conditions, which elements may exist as an independent atom in nature? Do you know? Well, yes, you have guessed it right. Noble gases. You also know that atoms are nature's building blocks. They combine chemically with variety of permutations, and a group of atoms found to exist together. So, what is such a group of atoms called? Come on, you can guess. Yes, it's a molecule. Now, the question is, which force holds these constituent atoms together in the molecules? This is the attractive force. So, the attractive force which holds various constituents, atoms, ions together in different chemical species is called a chemical bond. And we are going to learn about chemical bonding and molecular structure. Now, since the formation of these chemical compounds takes place as result of combination of atoms of various elements in different ways, it raises many questions. Maybe you must be thinking, why do atoms combine? Or question may come to your mind, why are only certain combinations possible? And why do some atoms combine while certain others do not? And perhaps some of you must be thinking, why do molecules possess definite shapes? To answer such questions, you will be learning different theories and concepts like causal Lewis approach, valence shell electron pair repulsion theory, valence bond theory, and molecular orbital theory. And you know that every system tends to be more stable, and bonding is nature's way of lowering the energy of the system to attain stability. So, let us begin with causal Lewis approach to chemical bonding. You have learnt in earlier classes about formation of NaCl from sodium and chlorine. Well, you can see it on the slide. Here, bond is formed as a result of electrostatic attraction between positive and negative ions. And what is this bond called? Yes, it's electrovalent bond, that is ionic bond. Now, the electrovalence, can you define electrovalence? The electrovalence is thus equal to the number of unit charges on the ion. So, similarly, in the formation of CaF2, tell me what is electrovalence calcium is assigned? Yes, a positive electrovalence of 2, while fluorine has a negative electrovalence of 1. So, this was Causal's first insight into the mechanism of formation of electropositive and electronegative ions, and he related this process to the attainment of noble gas configurations by the respective ions. Well, this electrostatic attraction between ions is the cause for their stability, and this gives the concept of electrovalency. And you know what? Lewis pictured the atom in terms of positively charged kernel. Now, you will ask me what kernel is. Well, he assumed kernel to be the nucleus plus the inner electrons and the outer shell that could accommodate a maximum of 8 electrons. And you know what? He further assumed that these 8 electrons occupy the corners of a cube which surround the kernel. Kozel and Lewis together developed electronic theory of chemical bonding. You know in which year? 1916. And they also formulated octet rule, which you are aware of. Well, the octet rule says that atoms can combine either by transfer of valence electrons from one atom to another, that is by gaining or losing, or by sharing of valence electrons in order to have an octet in their shell. Well, in 1919, you know what? Langmuir refined the Lewis postulations and he said, no, the idea of stationary cubical arrangement of the octet will not do, and he introduced the term covalent bond, and the process was again related to the attainment of noble gas configurations by reacting atoms as a result of sharing of electrons. Well, students, now this was a little of historical aspect. Now let us understand step by step how to draw Lewis structures and calculate formal charges. Well, now pick up your notebooks and start doing with me. Yes, the step 1 is we need to first count the total number of valence electrons. Now for example, if we take water, as you can see on the screen, H2O. So in water, each hydrogen has 1 electron. In 1s1, you know the electronic configuration, and we multiply that by 2. And oxygen, what is its electronic configuration? 2s2 and 2p4. So that makes 6 valence electrons. So we can add all those up and we get total 8 valence electrons. Now, what if we had cyanide ion? It is an anion. So for anions, each negative charge would mean addition of 1 electron. So here carbon has 4 valence electrons and nitrogen 2s2, 2p3 is the electronic configuration, remember. So nitrogen has 5 valence electrons, and here you have to add 1 extra valence electron. So that makes 10 valence electrons. Okay, so what about cations? How to go about adding the total valence electrons? I am sure you know by now. Come on, tell me. Yes, each positive charge would result in subtraction of 1 electron from total number of valence electrons. So, for example, if we have ammonium ion, NH4 plus ion, so 1 positive charge indicates loss of 1 electron from the group of neutral atoms. So, tell me, how many total valence electrons ammonium ion has? Come on, calculate and write down. And how about carbonate ions? CO3 2 minus. See, it has 2 negative charges. What do they indicate? Yes, that there are 2 additional electrons. So now it's your turn to calculate the total number of valence electrons. Okay, so you have understood this concept? Now, after counting the total number of valence electrons, let's go on to step 2. So step 2 is to determine the central atom. Now for this, you have to put the least electronegative atom in the center. Now how do you know which is least electronegative atom? For this, refer to the periodic table. Look here, fluorine is the most electronegative element in periodic table. So as we move away from fluorine, electronegativity decreases. Now if we consider NO2, nitrogen dioxide, look here, oxygen is next to fluorine and nitrogen still further away from fluorine. So, which will go in the center? Amongst nitrogen and oxygen, nitrogen is least electronegative. So, it goes in the center, as you can see on the screen. Now, tell me for PCl3, well, you just have to look again which atom is far from fluorine. So, phosphorus goes in the center. Yes. Now, moving ahead, step 3 is to draw a single bond. You know what single bond means? One shared electron pair between atoms to form a chemical bond. As you can see on screen, there is a single bond drawn between H and Cl, and on the side there is another HCl molecule where you can see 2 dots. This means 2 electrons have been utilized here for forming one bond. Okay, going ahead, we have step 4. Now, all you need to do is to complete the octet on the outside atoms with remaining number of electrons. So, out of 8 electrons in HCl, 2 have been used to form a bond between H and Cl, and rest 6 are drawn around Cl, as you can see on the screen, like this. Now, here hydrogen has 1 valence electron, chlorine has 7 valence electrons, and total number of 8 valence electrons. So, look, around chlorine we have 8 dots. So, in Lewis diagram, we have to use dots to represent valence electrons, and when you draw the dots, don't just put them anywhere. Instead, imagine a square drawn around the element, and the dot should be neatly drawn around 4 sides of the squares like this, with no more than 2 dots on each side. Yes, and children, practice drawing Lewis diagrams as much as you can of few elements till you get them right, because you are going to use these in VSEPR theory ahead. Okay, now coming to step 5. If any atom does not have an octet, we will have to move electrons from outer atoms to form double or triple bonds. Like you can see on the screen, that how a pair of electrons move from outside to inside in this oxygen molecule, and a double bond is formed. You know, that's how we get O double bond O. Now, in covalent bonding, atoms share valence electrons in order to get a full octet, or maybe duplet for hydrogen. And remember, shared electrons are counted as owned by both the atoms. You know why? Because they both satisfy the octet rule. Now, sharing of an electron pair between 2 atoms forms which bond? Yes, single covalent bond. And sharing of 2 or 3 electron pairs, that will result in formation of double or triple bond. Yes, the multiple bonds. So, do you know, some bonded atoms have additional pairs of electrons which are not involved in bonding. So, they also are represented with 2 dots, and what are they called? Well, they are the lonely pairs, not used in bonding. So, they are called lone pair of electrons. Okay, so now you can define what actually Lewis dot structure shows. A Lewis dot structure shows the arrangement of bonded pairs and lone pairs around each atom in a molecule. Now, here is a task for you. Let us apply this understanding and draw Lewis structures. So, come on, let us together learn to draw few Lewis structures. Well, so let us start with carbon dioxide molecule. So, let us try doing it. So, what you have to do? Step 1, you remember, count valence electrons. So, carbon 4 valence electrons, oxygen has 6 into 2. So, that makes 16 electrons. So, let us arrange these 16 electrons around carbon, and carbon is the least electronegative atom between carbon and oxygen. So, now after drawing the first structure, both the oxygens you can see have octet around them. But observe carefully, does carbon also has octet? Oh, it is short of 4 electrons. So, what we can do? Let us figure it out. Yes, we can shift these outer electrons inside. Wow! Now all are happy. They have their octets complete. So, that is how you can yourself draw Lewis structures of various molecules. And keep in mind, you need to keep practicing drawing of these Lewis structures. Now, here you have a worksheet and this is for you to complete. In the worksheet, as you can see, in one column you have molecules. In the second, you have to count the number of valence electrons and write down. And in the third, you can make space according to your own requirement and draw the Lewis structure. So, you can draw Lewis structure of carbon monoxide, that is CO, BH3, NO3 and maybe oxygen. So, try doing it. Okay. But now moving further, have you noticed one thing? Often you have more than one possible Lewis dot structures, and this happens when you have sulfur. Now, can you tell me which period sulfur is present in? Quickly you can refer to your periodic table. Yes, it is present in third period, and it also happens with phosphorus. That also belongs to the same period. So, they can have more than 8 electrons around them. Like you can see on the screen, you have 2 structures of sulfur dioxide. So, out of these 2 structures of sulfur dioxide molecule, now which one is stable? Well, you will say the one with the lowest energy, but natural. But how can you tell that yes, this is the one which is having lowest energy? It is very feasible. It is feasible to assign a formal charge on each atom. Let us calculate formal charge. And for calculating formal charge, you have to use the formula which you can see on the screen. Well, what does it say? It says formal charge on an atom in a Lewis structure is equal to total number of valence electrons in the free atom minus total number of non-bonding electrons, that is the lone pairs, minus total number of bonding, that is shared electron, divided by 2. So, let us use the formula and calculate the formal charges in the given these two SO2 structures. If we consider the first oxygen, it has 6 valence electrons and 6 non-bonding electrons, and look here, 2 bonding electrons, this we can divide by 2. So, what total we get is minus 1. So, let us write minus 1 charge on the oxygen. Now, moving to sulfur. Sulfur has 6 valence electrons, 2 non-bonding valence electrons, and look here, 6 bonding electrons. So, it is 6 by 2. So, the total is plus 1. So, let us write plus 1 on the sulfur atom. Yes, and the other oxygen, it has 6 valence electrons, 4 non-bonding valence electrons, and how many bonding valence electrons? 4, which you can divide by 2. So, the total comes to 0. Okay, so this was the first structure. Now, let us consider the other structure. Now, look here, oxygen has 6 valence electrons, 4 non-bonding valence electrons, 4 bonding electrons. So, the total is 0. So, it is 0 charge on oxygen. Next, we have sulfur. So, sulfur has 6 valence electrons, non-bonding electrons are 2, and bonding electrons 8. So, that goes 8 divided by 2. So, the total is 0. And putting this in formula, what we get? 6 minus 2, 8 divided by 2 is 0 charge. And lastly, the last oxygen. Now, here it is 6 valence electron minus 4 non-bonding electrons minus 4 bonding electrons divided by 2. So, that makes 0 again. Now, when we look at these structures, we would like to choose a structure whose formal charge is close to 0. You know why? Because formal charges help in the selection of the lowest energy structure from number of possible Lewis structures of a given species. Now, generally the lowest energy structure is the one with the smallest formal charge on the atoms. So, the formal charge is a factor based on pure covalent view of bonding, in which electron pairs are shared equally by neighboring atoms. Now that you have learned the octet rule, well students, now that you have learnt to calculate formal charges, always keep it in mind. Whenever you get more than 2 Lewis structures, you must always calculate the formal charge and choose that Lewis structure which has formal charges somewhere near to 0, because that Lewis structure only will be little real to the actual structure. And now that you have also learned the octet rule, you should note that though it is useful, but it is not universal. It applies mainly to the second period elements of the periodic table. Now, let us look into 3 types of exceptions to the octet rule. First one is that sometimes in some compounds there is incomplete octet of the central atom. Now, that means the number of electrons surrounding the central atom is less than 8. Now, my dear learners, this is especially the case with elements having less than 4 valence electrons. As you can see on the screen, the structure like lithium chloride. Yes, see how many electrons are there around the metal, and second is BeH2, and we also have boron chloride, BCl3. Now, looking at these structures, I am sure you must be wondering that lithium, beryllium and boron, they have 1, 2 or 3 valence electrons only. So, how come the structure is stable? Just ponder over and explore. And then there are also some other compounds like aluminum chloride, that is AlCl3 and BF3. So, it is time for you to draw their structures and explore a bit to find out how this structure is stable in spite of being electron deficient. Well, I am sure you can do it. Now, coming to the second exception, there are odd electron molecules also. In molecules with an odd number of electrons like nitric oxide NO and nitrogen dioxide, that is NO2. Now, see their structures on the screen. The octet rule is not satisfied for all the atoms. So, these are also exceptions. And lastly, let us consider another exception, the expanded octet. Can you recall from which period filling in the d orbital start? Well, I am sure you remember that elements in and beyond the third period of the periodic table, they have, apart from 3s and 3p orbitals, which orbitals are available for bonding? Well, yes, 3d. So, 3d orbitals are also available for bonding. Now, can you tell in compounds of which elements there are more than 8 valence electrons around the central atom? Think a little, I am sure you all know. Yes, compounds like PF5. Now observe carefully the structure of PF5 on the screen. Now look at the next structure, SF6. Now here the central atom is sulfur, and this sulfur also has more than 8 electrons around it. So what is it? This is expanded octet. And see, look at the third molecule here, H2SO4. Here also you must be wondering that sulfur is not obeying the octet rule. And there are number of other coordination compounds. So now you have observed their structures properly. So all of these have expanded octet, that is more than 8 electrons around phosphorus and sulfur. So obviously the octet rule was not applying in these cases. So they all are exceptions. Now here is a little task for you. You must explore and find out why is it so. Interestingly, sulfur also forms many compounds in which the octet rule is obeyed. Find out which compound is it. And now you have to do a little bit of research. Read from internet, visit libraries and read from your textbook, or you may refer to the QR code of your textbook, that how important parameters associated with chemical bonds like bond length, bond angle, bond enthalpy, bond order and bond polarity, how all of these have significant effect on the properties of compounds. Well, now coming to some drawbacks of the octet theory. It is clear that octet rule is based upon the chemical inertness of noble gases, which we had talked in the beginning. You may explore further and find out, well, how come these compounds are formed? Xenon fluoride, krypton fluoride, and I am sure you will see that this octet theory is not so perfect. And now one more important question. Can you tell the shape of the molecules with the help of octet theory? No, we can't. So this theory does not account for the shape of molecules. So this is another drawback. Now children, a small task for you. You know why this octet theory is not perfect? Well, ponder a little. So when scientists realized that sometimes many molecules and polyatomic ions cannot be described accurately by a single Lewis structure, so they wondered and thought of alternative explanation. Why don't you read about Kekulé, the scientist, and the story of how the idea of various structure of benzene rings came into his mind? Yes, here I want to say that it's interesting to read the historical aspect of creation of various theories and keeping a record of timeline frame. I'm sure you'll be inspired by them. So now coming back to the topic, whenever a single Lewis structure cannot describe molecule accurately, then a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as canonical structures of the hybrid, which describes the molecules more accurately. Now look at the screen. You can see the resonance in the ozone molecule. In structures 1 and 2, we have single bond between 2 oxygen atoms and a double bond between another oxygen atoms. Explore how they arrived at the hybrid form. Take this task a little further and try to explain the structure of carbonate ion in terms of resonance. So, what you have learned so far? Well, after going through this lesson, you will be able to explain electronic theory of chemical bonding developed by Kozel and Lewis. Based on octet rule, you will be able to draw Lewis structures of simple molecules and take initiative to know more about scientific discoveries. So, children, happy learning.